Hello, we are Yıldız Rover team from Yıldız Technical University, Istanbul, Turkey. This year we proud to present our 5th generation rover, OASIS.
Yıldız Rover was founded in 2018, and since then we have actively participated in national and international competitions, such as URC, ARC, ERC, and Technofest.
Throughout this journey, we have achieved various accomplishments, including the Autonomous Driving and Control Special Award, Best Astronaut Award, Presentation Award, and several first-place finishes. Beyond being a team focused solely on competitions, we organize the Rover Up event to contribute to the development of the rover ecosystem in Turkey. Our team carries out its work in the workshop located at Yıldız Technical University Davutpaşa campus. Using 3D printers and various manufacturing equipment, we conduct most of our prototyping and production processes in-house. The workshop also serves as a collaborative and research-oriented working environment. We utilize campus facilities for rover assembly and conduct tests that simulate real competition conditions. For task planning and team coordination, Google Calendar and Notion are actively used, enabling clear task distribution, effective timeline tracking, and rapid adaptation throughout the process.
We have now begun testing the rover, drawing on the experience gained this year. The tests have led through scenarios. Based exercise how the astronaut will respond in emergencies, the operator's familiarization with the rover, and the vehicle's overall capabilities.
Our rover is built on a lightweight and modular aluminum T-slot chassis, providing high rigidity while maintaining low weight. This structure also enables fast maintenance and rapid subsystem integration during competition preparation. The rover measures 1100 mm in length, 1000 mm in width, and 1400 mm in height, with a total mass of 55 kilograms. This year, the mobility system was fully redesigned with independent suspension on each wheel. This design ensures continuous ground contact on uneven terrain, significantly improving traction, stability, and maneuverability, while reducing vibration.
The rover is equipped with airless wheels featuring spoke structured rims which reduce overall weight while increasing structural rigidity. The wheel tread has been specifically optimized for runner-like fine-sand, maximizing grip, slip resistance, and long-term durability under abrasive conditions. High-performance brushless motors ensure precise speed control and high torque output for reliable operation on rough terrain and during sudden load variations. Our rim design is compatible with two motor options, Sky Air L228 and AK70, providing flexibility in performance tuning depending on mission requirement and terrain conditions.
Our robotic arm is a 6-degree of freedom manipulator designed for precise and reliable task execution. The first axis uses a worm gear mechanism selected for its self-locking capability and strong torque holding performance. The second and third axes utilize cycloidal reducers with brushless motors, allowing compact design with high torque output and minimal backlash for accurate motion control. The arm is constructed from aluminum, has a reach of 1200 mm, can lift over 5 kg, and has a total mass of 12.9 kg. A two-finger gripper enables safe and efficient handling of wide range of objects.
For ARC’26, several important improvements were implemented in both mobility and manipulation systems. In the manipulation system, the third axis was upgraded to 25:1 reduction system, increasing torque capacity and improving control under load. Additionally, the fourth and fifth axes now use steel-reinforced timing belts, enhancing precision, durability, and motion smoothness. In the mobility system, the optimized airless wheels and tread design improve performance on loose, fine-grained terrains such as lunar-like sand. These upgrades allow the rover to perform complex mission tasks more reliably, including carrying objects, opening containers, operating mechanical systems, and executing science-related operations in challenging field conditions.
OASIS is powered by 6 Series 8 parallel 24-voltage battery pack. Lithium-ion batteries were preferred for power efficiency and durability. A custom power distribution board steps down the battery voltage to 12 volts and 5 volts rails for the subsystems. The main computer Jetson Orin is powered by a separate LiPo pack to isolate mission-critical computing from drivetrain-induced power fluctuations.
Internal communication is made with CAN bus and handled by the Jetson Orin.
The choice of CAN bus provides EMI, EMC in communication line, while the main hub PCB maintains a link between Orin and STM32-based custom boards. This year, spare CAN lines are also utilized for reliability in case of a communication failure. UART, SPI, I2RC, and BASSC are used for mission-specific tasks.
For rover to base station communication, two frequency bands are utilized.
The 5.8 GHz band is used for high data rate transfer and video transmission, while 2.4 GHz is used for out-of-sight, long-range communication. The antenna structure was designed to allow easy switching between both bands during the missions.
The emergency stop button instantly disconnects all power, shutting down the rover completely.
An array of LEDs and night vision IP camera were integrated into the electronic system to improve visibility and environmental awareness during the night mission. The LEDs mounted on the upper and the lower section of the rover provide clear night vision into the designed area for the night mission.
As the science team, this year we researched the region's geology and astrobiological potential, then planned our hypotheses and field measurements based on our findings.
Our science period is about 4 kilograms and is safely integrated on the rover with a drill, sealed containers, sensors, and near-infrared reflectance spectrometer.
The rover takes panoramic images of the area to observe its surface and geological features. GMARS, MOLA, and CTX images were used to understand the region and shape the science hypothesis.
Soil samples are collected with a drill system on the rover from at least 15 centimeters depth and with a minimum mass of 10 grams. The sample is transferred to closed and sealed containers integrated into the drill mechanism and protected during the mission.
Soil and atmospheric sensors are used to measure field conditions, compare sampling areas, and test our hypothesis. We use a near-infrared reflectance spectrometer because it supports our hypothesis and helps us examine rock and soil samples. A microscope, muscle color chart, and rock archive are used.
GNSS data is obtained from the onboard GPS model, and rover navigates autonomously toward predefined waypoints. Using extended Kalman filter-based fusion of GPS, IMU, and wheel odometry for accurate localization. Within our extended autonomous navigation stack, we augment standard Nav 2 with lighter base, a layer 2.5D to reversibility layer for safe navigation on uneven terrain. A CPU accelerated trajectory optimization controller evaluates multiple candidate paths considering terrain slope and roughness to reduce rollover risk and generate optimal velocity commands, while high-level decisions are handled by behavior tree architecture.
An OpenCV and yellow-based vision system processes RGBs for object detection, while stereo depth enables precise 3D localization. During the surging state, the rover operates autonomously using data from Z stereo cameras mounted on both the upper body and beneath the chassis. The lower Z improves visibility of ground-level objects while scanning the environment. Initial testing and validation were first performed in the simulation using our custom URDF modeling as above.